Hi everyone, really good to see you today. Matthew Kennedy here from Module 9 discussion where we're talking about the foundations of mathematics. Hope you're having a great day. We'll get right into it. So you have explored the history of mathematics from antiquity to modern day in this course. How do you feel about the foundations of mathematics? Explain what you mean and provide examples/illustrations and multiple connections to course material to back up your perspectives. So the one thing I'll say from this module is it's really almost the end of a language. The BBC video said it perfectly. They really explored all the way back from the Egyptians of a number system to all the way to Hilbert and Cantor with these pretty advanced proofs with infinity and other pretty much advanced mathematical concepts. We think about the foundations of mathematics. We think about how really it's a whole language. Math is a language. It's a language of patterns and numbers and shapes and a big question of why. And really, you think about math as a language with the English language. You think about how in English language they created words. They then define the words. Actually, we can say they created the words. They then spell the words. They define the words. They then create sentences from the words. They then create grammar rules to make the sentences smooth, to make it universally accepted. Commas are used for this and this. Whoever made commas, they could have made it this way. Instead, they made it this way, right? And then putting it all together, can we utilize that English language to write a perfect essay? That's how mathematics is. We start from the number system. We start from saying this shape, it's a circle. Someone could have said that shape is and we would have called it but they said the word circle, so that's what we use, right? Someone had to use and create these foundations of this language, and then it evolved from there. We then used that circle, and we did things with it. Pi was evolved, just like grammar was evolved for these sentences. And the end result in the English language as a language was, how can I really perfect, this English language? How can I really perfect it in a way where I can show my skills and I can show you that I understand, grammar, words, good synonyms, sentence structure. That's writing a whole essay. In math, it's proofs. Can I show you I understand, algebra, calculus? Can I understand geometry, even trig, in such a way that I can prove to you that I know this, and I can, and really this is like probably the most advanced step, and we can say it on Bloom's taxonomy. It's the highest step because it's really the definition of applying and synthesizing, because you're not only you're not only knowing the answer. Prove what? I can prove that this set is infinite. Okay, nice. You know this says infinite. Nice. But can you prove it to me? If you can prove it to me, you have shown me you have mastered that language. And I think really math is cool in a sense where, let me share a story. So I was in the field and for my Methods 1 placement, and I was talking to one of these teachers, and her name was Miss K, and she said, pre-calc is actually one of the most struggling subjects in math for high school students. I said, well, why, Miss K? Because it was the most struggling for me as well. And she goes, well, you really think about what pre-calc is. It's before calculus, which is really a new language, and then it's after algebra, geometry, and trig. Pre-calc is the end of the language. It's Spanish 4, if you will. Right before you go into French 1 of a new language of calculus. Pre-calc is algebra, geometry, and trig on steroids. It's pretty much saying you are going to pretty much end this language. there's no calculus, like there's no derivatives, there's no integrals. Pre-calc, there's not, like maybe inverse trig, like maybe that's new. Like there are some new concepts in pre-calc, but it's really, like you already know most of the concepts. Pythagorean theorem, patterns in algebra, series. Like pre-calc, we already have seen concepts in pre-calc from previous subjects, again, algebra, geometry, and trig. It's just putting it all together before you go into calc. And you really think about that, that just shows you, like directly actually, how math is foundational and it's layer upon layer upon layer. And then you go to pre-calc and it's like, oh wow, here we are. Like, if we get through pre-calc, we really showed we know our algebra, geometry, and trig game. We then go to calculus, which actually uses all of them, but it's not really as, I guess you can say, extreme as pre-calc. Like pre-calc really makes sure, it makes sure you know what algebra, geometry, and all that stuff is. But we now go into really, after calculus, we talk about, calc 1 to calc 2. In calc 2, we know what an integral is. It's area under the curve, antiderivative. You then have bounds of integration. You plug in, subtract from the bounds of integration. And that's your area under the curve, right? But then calc 2, we bring in some maybe multivariable, right? Well, that's calc 3, but we have integral by parts. We have the trig substitution integrals, right? We have series, which we kind of had heard about series in Algebra 1 and pre-calc, but now we're getting more into like geometric series. We're getting more into, okay, does it converge, diverge, right? Really some more applicative thinking, right? After calculus, we then go to discrete math in the proof-based, which really was the foundation of this module. From Hodgkin, chapter 9, here's some of my connections to reading. Given a set of sets x sub of a indexed by, this is page 219 by the way, indexed by a element of a, there exists a function f on the indexing set capital A such that for each a f of a is an element of x sub of a. So that's pretty confusing to hear that, verbally here. But what it's saying is you can really prove things in mathematics by mapping one element from one set to another element in another set, such that if it's one-to-one and onto, you can really prove that the cardinality of those two sets are essentially equal. Maybe it's finite, maybe it's infinite, right? So that was really a big takeaway. And also from the BBC video, the Riemann hypothesis, prime numbers. 31 is a prime number. 37 is the next prime number. After that, how can I figure out the next prime number from a formula? There's no such formula that exists. It's an unsolved problem. And number theory is big on patterns, exploration of intuitions. And you really think about number theory, that was a big topic with proving infinity. Again, 1, 2, this is from the BBC video again. 1, well, it was a little bit of the second video too. The second video is about fractions too, and how we can really map fractions. So like, for example, like row 2, column 7 is like 2/7. Or column 9, row 19 is 9/19. We can map things visually and prove it that way. And as you can see, if we were to go to infinity plus 1 to, or infinity this, it would be this, right? So like math has evolved from foundations. It gets more advanced and more advanced and more advanced all the way to the end where here we are, Cantor and Hilbert. We have all these problems. I have 7 bridges in the BBC video. How can I go through each bridge once, okay, and still make it? How can I go through all the bridges, 7 bridges, without going through one bridge twice? And that problem was proved to be incomplete. You can't do it. So math has now, like, it's just amazing how the language works. It's amazing how we go from these foundational roots of a number system, zero, the Euclid Book of Elements, even algebraic developments of symbols, other stuff, basic calculus with integral derivatives back in the Leibniz and infinitesimal of Newton, all that stuff. And now here we are in the 20th and 21st century. Now we're really exploring things like, how can I really prove and try to figure out that next prime number? How can I prove why, this cardinality of this set is this? And also a thing from the reading too that stood out to me was the part of the reading where it talked about consistency and completeness of a function. So is it possible, given any formula P, to determine if it is true or false? So you have to literally create formulas that prove whether a system is consistent or inconsistent. It's things like that that makes math now so complicated, where it's like, yeah, we have the foundations down now. We already discovered and created pi. We already had a number system created of base 10. We have a metric system. We have, all these, algebraic, roots, quadratics, binomials, trinomials, all this stuff just down. Now it's taking it a step further, how can we prove this stuff? And that's really where the foundations of mathematics is taken off. So I don't make the video too long, but really the goal of this video is really talking about how we go from all the way back then, where things were just evolving. Things were being just created, just like the English language was. And look where it took off. Look where we are today. As math students, K through 12, we learn the number of systems. We then learn about equations for the first time in, 6th, 7th, 8th grade. In high school, an equation is just a fraction of algebra, geometry, trig. And then ultimately we go to calculus, and then if you go past calculus, a lot of proof-based thinking, right? Modern geometry here at modern algebra, modern geometry. How can I prove that this mapping is a one-to-one function? Or how can I prove that in modern geometry that the minimum of this distance is only a minimum if this triangle is isosceles? Well, it's because of this and this and Heron's theorem and this. Math is applicative. It's a language. We have to use previous foundational knowledge to prove the broad scope of the idea that this will always work for all n, or etc. So that's really my takeaway from this course, is really how foundational, how layering math is. And it will always be a layer. There will be layers in the future to come. We just can't see it today. It's like saying 50 years ago, Steve Jobs with the iPhones. Like, I guarantee you 40 years ago, everyone said, oh my gosh, the first computers, this is so advanced. I don't know how much more advanced it could be. Yeah, it got way more advanced. So, same thing with mathematics. Maybe someone will solve the Riemann hypothesis one day. Maybe they won't. But years from now, if the Riemann hypothesis is ever solved, it just shows you math is an ongoing process, and it's still a language that has not been complete and probably will never be complete. As ironic as it sounds, and without making it a huge pun and all that stuff, math is a language that literally is infinity. It will never be finished. And infinity and infinity proofs were a big part of this module as well. So that's kind of like I said, all right, I'm gonna end it. All right.